This lesson is how to find areas of regular polygons. This is lesson 11.4. And you already know how to find the area of one kind of regular polygon, a square. So that can be treated either as area side squared, or it can be considered to be a rectangle, which is length times width, or you can do the rhombus formula, which is 1/2 diagonal 1 times diagonal 2. Now, this lesson will actually give you another way to find areas of all different kinds of regular polygons, and the first one being an equilateral triangle. So, area of a triangle in general is 1/2 base height. That's a formula that we already knew. But we're going to derive some other formulas here. So, another formula here. So, for an equilateral triangle, remember that since area is 1/2 base height, I would need to drop an altitude. Here, if we were going to consider that the height to the base being one of the sides. Now, if you consider the side lengths to be s, then when you drop the altitude, each of these would be 1/2 of s, or s over 2, whichever way you want to think of that, 1/2 s or s over 2. And then because this was originally equilateral, we know all these angle measures would be 60 degrees, which would cause those two triangles to be 30, 60, 90 triangles. So looking at just this triangle on the right side here, that would make the short leg half of the original side of the triangle, and it would make this altitude here the short leg times root 3. So s over 2 times the square root of 3. Now, when you go to do 1/2 base height, that means that you would be doing 1/2 times the base, which is the whole entire side length, the red segment, times the height, which is s over 2 times the square root of 3. Now, just to make sure we remember everything that's in the numerator there, I'm going to put those over 1. So if you just multiplied those straight across, the top would become s squared root 3, and the denominator would be 4. So that is a new formula which works to find the area of a triangle that is equilateral. This is only for triangles that are equilateral. So only for equilateral triangles. No other kind of triangles, no other kind of equilateral polygons, only equilateral triangles. Now, usually what happens is when we're doing a lot of equilateral triangles, you guys will be pulling out the s squared radical 3 over 4 formula, and then as soon as we kind of stop doing it for a while, you go back to do areas of a non-regular triangle, and you'll start trying to use this formula because you've been using it on the regular polygons. If you want to learn this as root 3 over 4 times side squared, that's okay too. Those are the same thing. So if you want to think of it as a multiple of the side squared, or just learn the formula s squared root 3 over 4, I probably use the s squared root 3 over 4 more. Okay, so here's an example. If you have this equilateral triangle, remember this formula is only for the area of an equilateral triangle. So the area is s squared root 3 over 4. The side is 8, so it would be 8 squared root 3 over 4, which is 64 root 3 over 4. And then remember, you can simplify the numbers on the outside, so it becomes 16 root 3. That would be centimeters squared. Okay, now you could still, if you wanted to drop the altitude and go through kind of the process I just did, you can treat that. That's 4, that's 8, so this is 4, so this is 4 root 3 over 3, and you can do 1/2 base times height would be 4 times 4 root 3 over 3, and get 16 root 3. It sort of depends on how nice this number right here is. If I give you not a very nice side length, it might be easier to use the s squared root 3 over 4 rather than the 1/2 base height. So it's just another formula to put into your toolbox. Remember, you should have a toolbox with all these different formulas so you can pull them out when you need them. Okay, so moving on. Now we're going to be talking about more general kinds of regular polygons. So the rest of this will not be focusing on just equilateral triangles, but this will be general regular polygons. So you can use this process on an equilateral triangle because it's regular, or any other kind of regular polygon. Now, remember that regular means equilateral and what? Equiangular. So it has to have all congruent sides and all congruent angle measures. So just remember that's the definition of a regular. Okay, so a regular polygon can always be inscribed into a circle. So the what you got here is a hexagon. I had to pick a certain number of sides, and I described a hexagon when I was drawing this picture. So I've circumscribed a circle around the polygon, which means the polygon is inscribed in the circle. Okay, so some terminology. The center. The center of a regular polygon is the center of its circumscribed circle. So if you look at the fact that circle S is a circumscribed circle, that will make S the center of the circle. So in this picture, S is the center of our polygon. The radius of a regular polygon. The radius of a regular polygon is the radius of its circumscribed circle. That's easy enough, right? A radius would go from the center to a vertex. So in this picture, are there any radii drawn? Well, yes, I've already drawn for you this radius and this radius. Now, how many more radii would there be? Okay, the polygon's radii go from the center of the polygon to its vertices. Now, you'll notice that each one of these radii will cut the regular polygon into triangles that are all congruent to each other. Because this is a hexagon, that means that there will be 6 congruent triangles. If it was an octagon, for example, there would be 8 congruent triangles. Okay, but in this picture, segment SX and segment SY, for example, are radii. So segment SX and segment SY, those are the radii in the regular polygon. Now, there's something called, this is a term I'm sure you haven't heard before, there is something called, you can either call it an apothem or an apothem. I usually call it apothem, but you will hear some teachers, even some teachers at cathedral, will call this an apothem. So that's simply the distance from the center of the polygon to any side. Okay, it's an irregular polygon, the distance from the center to any side. So what does that really represent? Well, it's the altitude of one of those triangles. So the apothems would be all the segments that would be perpendicular from the center to a side of the polygon. So it's just simply, again, an altitude of each of those triangles. So I'm just going to leave that first apothem there that's drawn. Segment in this picture, segment SW, is an apothem, and there would be 6 apothems in this one because there are 6 sides. So there's 6 sides to draw a segment perpendicular to from the center. Okay, and then lastly, a central angle. You've heard that term before. So a central angle of a regular polygon is an angle with its vertex at the center of the circle and whose sides contain 2 consecutive vertices of the regular polygon. So in this picture, this angle right here is a central angle. Now, if you wanted to figure out the measure of that central angle, well, for this polygon, it would be 360 divided by what? Well, if there's 6 congruent triangles, they would all be, those central angles would all be congruent, so that would be 360 divided by 6. Now, in a generic triangle, I'm sorry, a generic regular polygon, it would be 360 divided by however many central angle measures there are, and that's the same as the number of sides. So 360 over n would be the measure of one of the central angles. So angle YSX is a central angle of the polygon. And again, there are 6 central angles. Now, notice that it says the vertex is the center and the sides have to contain 2 consecutive vertices. So for example, if you were just talking about the circle S, this angle right there, that would be a central angle because this vertex is the center of the circle. But for a polygon, that is not a central angle. Okay, central angles are, you want to think about drawing in all the possible radii, and then if you look at one of those angles in the center, that is this, again, has a measure of 360 over the number of sides. This is the measure of each of the central angles. .360 over the number of sides would be the measure of each central angle. Okay, now we're going to derive this formula that is how to find the area of any regular polygon. So this is helpful for, again, you can use it for squares, you can use it for regular triangles, but you can use it also for any kind of regular polygons. No matter how many sides there are, if it's equilateral, equiangular, you can use this formula to find the area. I wanted to go back up here for a second. I want to make sure that we point out the distance here is the perpendicular distance. So make sure that when you're looking for the apothem, you're looking for the altitude of the triangles. And then again, down here for the central angle measure, the central angle measure will be each central angle will be 360 divided by n, where n is the number of sides. Okay, so suppose that we wanted to find the area of this regular hexagon. We could find the area of one of the triangles and then multiply by how many triangles there are. And we could always do this. You can always take a regular polygon and split it into n, if there are n sides, split into n congruent triangles and then find the area of one of them and multiply by how many there are. But what we're going to do is derive a formula so we don't have to kind of go through that process every time. So the area would be the area of one triangle multiplied by the number of triangles. Well, this is the area formula, right? 1/2 base height is the area formula for any triangle. The number of triangles is the same as the number of sides in the polygon. That's your n value. Okay, so now if you think about kind of the base height idea, the base length is simply the length of one of the segments of the polygon. So it's the length of a side. What's the height? Well, the height of each of the triangles is the apothem. And then the number of sides, again, is your n value. So if you multiply the length of one of the sides by how many sides there are, if you multiply, like let's say each one is 10 units long and there's 6 sides, what are you finding when you do that? Well, each side is 10, there's 6, that's the distance around the whole thing, that's the perimeter. I'm kind of running out of space here. This should be a little bit higher. Okay, so that is the perimeter of the polygon. And then if you just carry along that 1/2, we've got the 1/2 from above. Our apothem is carrying along, so we've got the apothem is again the altitude of one of the triangles multiplied by the perimeter, and that's our formula for a regular polygon. Area of a regular polygon is 1/2 times little a, which represents the apothem, times capital P, which represents the perimeter of the regular polygon. So, area formula for a regular polygon, any regular polygon, is 1/2 apothem times perimeter. 1/2 AP. 1/2 looks kind of weird. There we go. 1/2 AP. Okay, so area formula for any regular polygon. Now again, you could use this for a square. You could use this for an equilateral triangle, but there's another formula that you have to use. So 1/2 AP is for any regular polygon. In our toolbox, we want to file that away under regular polygons. Okay, so a couple of examples. Find the area and perimeter of a regular hexagon with an apothem of 5 root 3. Now again, you need to understand what an apothem actually is so that you can kind of work your way through this problem. I've given you a little hexagon there to draw on because sometimes it's easier when you have a nice regular looking figure. So a hexagon has how many sides? First thing you want to note is the number of sides in your regular polygon. We know it's regular, it has 6 sides. Okay. After you kind of take note of what the picture is supposed to look like, you want to make sure you've drawn everything on the picture. Our apothem is supposed to be 5 root 3, so from the center of the polygon, perpendicular to one of the sides, is supposed to be 5 root 3. Okay, so our apothem here is 5 square root of 3. Okay, now, we want to figure out when you draw in these triangles, what color are my triangles up here? They were pink. Okay, so when we draw in these triangles, we want to know what kind of triangle measures we're looking at. So you want to figure out what would the central angle measure be. Now, you don't actually need all of these radii. Remember, these are radii because they're radius of the circle. You don't actually need all the radii, but it kind of helps to think about the fact that these would be 6 congruent central angles, right? Which means the central angle measure, I should use orange for central angle. So the measure of each central angle is going to be 360 divided by the number of sides. So 360 over 6 is 60 degrees for each central angle. Now that means that here we have each of these pink angles is 60 degrees. Okay, so when we drop in our apothem, this little triangle is kind of the triangle that you want to be focusing on here. So this little triangle right here. We need to find some information. Now remember, for perimeter and for area, those are the two things that they're asking us to find. We need to have some more information. So what does perimeter require? Well, we need to figure out what are the side lengths. What does area require? Well, area formula was 1/2 times the apothem times the perimeter. We know the apothem, we're good there, but we don't know the perimeter, which means we need to find the side length. Okay, so let's go back to here. We made a 60-degree central angle, cut that in half, is going to be 30 degrees. I don't really think I really want to highlight my 60 there. Okay, so 30 degrees is our central angle measure. Sorry, not our central angle, our angle right here. Okay, now some people kind of prefer to say you're going to take the central angle and divide it by double the number of sides. So if you took 360 and divided it by 12, you'd get directly to 30. I think it makes sense to go through the process of saying how many sides are there, cut it in half. That's going to be the angle measure that we need. We don't really need the central angle, but we really need half the central angle. Okay, which means we're looking at a little 30, 60, 90 triangle here. Now, if the apothem is 5 root 3, and that's the long leg, how long would the short leg be? Well, 5 root 3, we're going to divide it by root 3, right? That's just 5. Now, how long is the side length? Well, a side of the polygon, the whole thing is going to be 10. Okay, this point will always be the midpoint of where the apothem hits the side of the polygon. It will always be the midpoint. It will always cut these two parts in half into two congruent parts. Now, what will not always happen is this 30, 60, 90 triangle. Why did we get a 30, 60, 90? We got a 30, 60, 90 because we started out with the hexagon. Okay, is it ever possible to have another polygon with a 30, 60, 90 triangle? Well, only if the central angle measure up here, if this was 120 and that was 60, well, how could that happen? The central angle measure being 120 would happen in what kind of figure? Well, 360 divided by n being 120 means there had to be how many sides? Well, that would happen if there were 3 sides. So that's only going to happen if it's an equilateral triangle. In the picture, the 30, 60, 90 triangle will kind of be oriented the other way. You can also get 30, 60, 90s in equilateral triangles, but don't think that you're always going to end up with a 30, 60, 90 triangle because um, it's going to depend on what the central angle measure is. Now, back to perimeter. Our perimeter is obviously the length of a side times the number of sides. So our perimeter is going to be 10 times how many sides there are, 6. It's 60, and we don't have any units, so we're just going to say 60 units. Okay, and then our area formula is a 1/2 apothem perimeter. So it's a 1/2. The apothem was 5√3. Our perimeter, we just use the number we found, is 60. So do the perimeter before you do the area because you need the perimeter to get the area. Now when you multiply this, you can either do 5 times 60, which is 300, and then divide it by 2, which would be 150, and then carry along the √3. Or you can do half of 60 is 30, and 30 times 5 is 150, and then √3, and our label would be in units squared. Okay, so that's our perimeter and area for a regular hexagon. Okay, so to recap, you want to do the perimeter before the area. You need the number of side lengths so that you can figure out what the central angle measure is and then what the angle in the little triangle that you have will be. And you also need to pay attention to what kind of triangle that you have so you can work your way around and find the side length. Okay, last problem. Find the area of a regular pentagon that has a side of length 10 meters. Okay, so we've got a pentagon. How many sides? You need to know that in case I don't give you the picture. There's 5 sides. Now again, this is regular. This one just asked you for area, but remember I told you really need the perimeter to do the area anyway, so you might as well find the perimeter first. Okay, so we're going to calculate our central angle measure. Central angle is always 360 over the number of sides, which will be 360 over 5, and that's 72 degrees. Now you're going to cut that in half, which would give you 36 degrees. Now let me show you on the picture again why you do that. Central angle measure is from the center of the circle to with 2 radii out to the vertices of the polygon. Our apothem is going to go perpendicular the height of one of those triangles, and it's going to hit the midpoint of the side and make split our big triangle into 2 smaller right triangles. Now we need to know 36 degrees because we need to know that the large central angle measure, so if you drew in one of these actual central angles, that would be 72 degrees. We need to know, though, what this angle measure is. And that angle measure, I don't want to use green. That angle measure is going to be 36 because it's cutting the 72 in half. Okay, now I'm going to use R to represent radius, and I'm going to use A to represent apothem because a lot of times they might give you the radius value also instead of the apothem. Okay, now we know the side length is 10. So out here we've got a 10, which means that these sides will be 5 and 5. Now I'm going to draw you a nice bigger right triangle here. The side that you know is at 5, the apothem, for 1/2 apothem perimeter, the apothem is what we need, and we know we have a 36 degree angle here. Now, how do you find the apothem if you have 36 degrees and you have 5? Well, this is where trig comes in handy. Yay! Tangent of 36 degrees is equal to the opposite, which is 5, over the adjacent, which is the apothem. Okay, we're going to multiply both sides by A. Didn't mean to grab that color. Multiply both sides by A, and then divide by tangent 36. So your apothem, which again we need that to do the area because it's 1/2 apothem times perimeter. Apothem will be 5 divided by the tangent of 36. Now when you're using trig, you will not be able to give the exact answers. So we're going to go ahead and round this one. Let's go to the hundredths place. So 6.88 is our apothem. Okay, so I wanted to remind you that you're doing tangent there because SOHCAHTOA, tangent uses opposite and adjacent. All right, so we're trying to get the area. So perimeter first would be 10 is the length of a side. There's 5 sides, so that would be 50, and we're in meters. So that's our perimeter value. You know, and I'm going to move this down a little bit so we have a little more room to work. Okay, and then area is 1/2 times apothem times perimeter. So that's 1/2. Our apothem is 6.88 that we found down below. Our perimeter we just calculated is 50. Okay, that'd be 25 by 6.88. Our area, and this is really an approximation, so I'm going to make this approximately. So our area is approximately 172, if you multiply that out, units, or sorry, it'd be in meters squared. So again, to recap, you want to make sure that you pay attention to how many sides there are. It has to be a regular polygon. You want to start by finding the central angle measure and make sure you cut it in half, because you really want to focus on this little right triangle here. So you can do trig and Pythagorean theorem and special right triangles and all that kind of stuff. Okay, and then you need perimeter in order to do the 1/2 apothem perimeter formula. So calculate the perimeter from the side length that you find or are given, and then you can work your way through whatever trig or special right triangles calculations you need to do. This is the end of this video. Yay!